Next topic is liquid extraction. This is a very important topic. Here we are going to separate the components within the liquid in one phase and another liquid to another liquid. Okay, that is two different phases. One is aqueous phase and another one is that is organic solvent phase. Okay, the dielectric constant D of a substance can be measured by determining the electrostatic capacity. So this electrostatic capacity is C. Okay, that is C divided by C0. C0 is the value of the same condenser when completely evacuated. Okay, that means so the D is equal to C divided by C0. This is the value, and experimentally the dielectric constant are obtained by comparing the capacity of the condenser. Okay, that is D1 divided by D2 is equal to C1 divided by C2. So this is D1, D2 are dielectric constant of the experimental and the standard liquids. Experimental is the first one, the D1, and the standard is D2. And C1 and C2 are the electrostatic capacities of a condenser when filled with each of the liquid. When two liquids are there, okay, that may be applied. So finally the K, the partition coefficient K, is equal to the concentration of the solute in the extract and concentration of solute in the raffinate. Okay, and these two are the very important, the concentration of solute and the extract and concentration of solute in the raffinate. Raffinate means the penetrated one to the next liquid, that's called as raffinate. You can see here the raffinate is going to be transferred from one mixer to another mixer and another mixer to another mixer. Okay, there are three different mixers are there. So not only three, okay, this may be n numbers, maybe based on the co-current flow extraction system. Just you can feed, okay, the culture filtrate, and this will be the solvent, and add the solvent also, and you can remove the extract and the raffinate, okay, subjected for a second mixer separated by passing the solvent, and you can get the extract. Again this raffinate, okay, raffinate means, okay, maybe after getting the extract, the byproduct, the remaining product, so this has to be further extracted. So this raffinate again goes further steps. This is n number of times, and n number of times all the extracts will be collected. This is called as co-current flow extraction system. Okay, next one is the counter current extraction system. Counter current means, so this feed is passed through the mixer separator, and the raffinate is passed to the next mixer, and the raffinate goes to the next one n number of times, and depleted raffinate is removed, and at the same time in the opposite direction, okay, this solvent, okay, has to be passed to the last one and to the subsequent ones, and finally to the first one. The solvent enriched with the product, okay, can be collected from the one. So this is called as co-current. Co-current means, okay, this is in the opposite direction, raffinate direction, and also solvent direction is entirely different, and here raffinate and feed are both. Okay, raffinate and solvent directions are both are the same direction. So this is a table of dielectric constant at 25 degrees C. You can see the least polar is hexane and the highest polar is water. Not only water, the next to water is pyridine. Okay, this pyridine is the highest polar solvent, and so this is the dielectric constants. Just you can have a look. Okay, this is the separating funnel. You can see here, this is one phase and another phase. This is organic phase and liquid aqueous phase. This is organic phase. Okay, and this is a model of separating funnel. Usually you can mix it by manually, or otherwise in the large scale, okay, in the industry, okay, they will use a mixer by rotating attached with a rotor, and this will rotate by approximately 2000 to 3000 rpm. So this is solvent is added and aqueous broth is added, okay, mixing completely, and after the separation, okay, like this, there are two aqueous phase. This is bottom is aqueous, and the top layer is organic layer, and by opening the stopcock we can collect it. So this is called a single stage extraction unit, and I'll play a video, okay, by explaining the complete the principles of liquid extraction, just to have a look.
Today we're going to talk about extraction, and this is a lab technique you might use to purify a compound or to isolate a compound. And we're going to go through an animation that explores the process of extracting 3 times with ether, as you might do for a typical reaction workup. First, let's take a quick look at the equipment that we'll need to do a extraction. What we're using here is called a separatory funnel, or just a SEP funnel for short. It has a stopper that fits on top. This might be a ground glass stopper or maybe a plastic one. If it's ground glass, you want to use the smallest amount of grease here as possible because we don't want to contaminate our solutions with that. But a lot of times we have a plastic one up here, and down at the bottom we have a stopcock. This is a valve that's going to allow the liquids to flow out or keep them in. This is all going to be supported by a ring stand and a support ring that allows the SEP funnel to rest in it, and so we could take it in and take it out very easily without having to clamp it and unclamp it each time. Okay, inside the SEP funnel we're going to have two layers. We're going to have an organic layer and an aqueous layer, and typically as shown the organic layer is going to be the upper layer because most organic solvents are less dense than water. The exception there is when we have organic solvents that are halogenated like dichloromethane. That's going to be more dense than water, so we'll see it as the bottom layer. But typically the organic layer is going to be our top layer, and whatever we have dissolved in the water is going to be described as our aqueous layer. So let's go ahead and get started with our animation. What we have here is a reaction mixture that a reaction has been quenched by adding water, so it's now aqueous. It's got a lot of components dissolved in it, and we're going to pour that in. Again, if you want to use a funnel up here to pour it more carefully, that's fine, so we don't get any spilling. And absolutely you want to make sure that your stopcock is closed before you start adding liquids to it. And so, because sometimes we forget that, I think every chemist on the planet at one point has accidentally poured liquid into a SEP funnel with an open stopcock. It's really good practice to have a flask down here, just in case if anything ever even drips. Sometimes your stopcock is loose and things might drip even though it's at the closed position, or of course if you accidentally had it open. So we're going to add our aqueous layer, and then we're going to take some pure ether and pour that in. Of course that's going to create a top layer, and then we're going to mix the two layers. So we're going to put a stopper on top, and we're going to remove it from the support ring, and we're going to mix it gently at first and then more vigorously to achieve equilibrium. Okay, now as we did that, we noticed that I put you want to put your finger on the top of the stopper to make sure that the stopper doesn't come loose and nothing drips out of the stopper. It's held securely, and you also want to periodically open up the stopcock when the SEP funnel is upside down. Open up the stopcock to release any built-up pressure, any gases that may have formed. So as you're mixing, it kind of creates some gases, and especially when you're using something like sodium bicarbonate in your aqueous layer, that's most definitely going to generate some carbon dioxide and build up gases. So we want to vent it right away, and then periodically as we're shaking to make sure that we don't have any pressure that builds up. Okay, so we want to mix it thoroughly to achieve equilibrium, because during that process, the components that were dissolved in the aqueous layer, some of those are going to move to the organic layer, and we describe this process as partitioning. Now notice that not all of the organic soluble components have just raced over to the organic layer, only some of them. So this is described as the partition coefficient of that compound and how it likes to partition itself between an aqueous and organic layer. And that's what we're trying to achieve by mixing, is getting that equilibrium, whereas much of the component is going to move to the organic layer as it wants to. Okay, so we're done with our first extraction. We're going to open up the stopcock with the stopper removed. We can drain the aqueous layer, and then we can drain the organic layer. You can drain it through the stopcock as shown, but there's going to be some water that's trapped in the stopcock, and so a better practice is you can just pour the organic layer out through the top of the SEP funnel, and that way we're keeping our organic layer as water-free as possible. Notice too that we've labeled our flasks here. That's really good practice because it's very easy to kind of get mixed up on what's what, especially if both of these are clear colorless solutions. It's sometimes hard to remember which is which. Okay, so because the aqueous layer still contains some of our desired compound, we're going to do a second extraction. We're going to do multiple extractions. So we'll pour our aqueous layer back in to the SEP funnel. We're going to use another fresh portion of ether, and then we're going to mix these again. So add the stopper to the top, and while securing the stopper with our finger, we're going to mix it with periodic venting. Okay, now at this point, typically our organic and aqueous layers will nicely separate, And again, notice that most of the things here, another portion of our desired compound has moved over. But sometimes those two layers don't separate perfectly, and that's described as having an emulsion. If you notice that you are only getting one layer and not the two layers that you're expecting, there's a couple things that might have happened. One time is a very common mistake is if you had your aqueous layer in here and then you added more of an aqueous solution here, then of course you wouldn't get two layers. Or if you had your organic layer in here and that's when you added the fresh portion of ether, that's only going to give you one layer. So again, it's really important to keep track of what's what and make sure that's not why you got one layer. But if you've had two layers and then you mix them and after doing the extraction you still only have one layer, that's described as an emulsion. And so what we want to do is to break up that emulsion. A lot of times it's just being patient and letting it sit until they finally break up into two layers. Sometimes you can add a little bit of more organic, a little bit of more aqueous, so that might start that separation process. To break up an emulsion, you can also add a glass stir rod and stir things gently. Sometimes there's some fine particles in there or some kind of bubbles that you can break up. You can try adding some brine or some sodium chloride in there. So there's several strategies you can use to break up an emulsion if you have one. But once the two layers have clearly separated, then we can separate the two layers into two different flasks. Okay, so we're going to do a final third extraction, pouring the aqueous back in, another fresh portion of ether, trying to get this last little bit of our desired compound into the organic layer. So we're going to mix to achieve equilibrium, remove our stopper, and again, hopefully we're not forming an emulsion and these two layers separate nicely. We could drain our aqueous layer and then add the organic. Notice we're describing this now as our combined organic layers. So all of our organic extracts we're going to add back into the same flask so that we have all of our desired compounds here. Okay, now we have a few steps before we could get to our isolated extracts. Very often we have some washing steps, and so what's in this organic layer might have some contaminants in there that we can remove by doing more extraction processes. So we could pour this organic layer back into the SEP funnel, and then maybe we can wash it with some portions of water, or maybe we could use a dilute acid. If there's any basic components in here, a dilute acid wash would remove those. If we had any acidic components in here, or residual acid, we could wash the organic layer with a dilute base, and that would turn that into a salt, and that salt, of course, would prefer to be in the aqueous layer. So we might want to have some washing steps in here, and then finally we finish the extraction process by doing a drying process, and what that means is we want to remove any aqueous layer or water that is dissolved in the organic layer. So water does have some solubility in ether, and so we describe these combined organic layers as being wet with that dissolved water, so we treat it with a drying agent. We could wash it with some brine, some saturated sodium chloride. That would remove most of the water, but then to remove the trace amounts of water, what we do is we add a solid drying agent. So we just add, we put our solution in an Erlenmeyer flask as shown. We scoop in a small amount of solid drying agent and then swirl it around, and that's going to absorb any dissolved water. And after we let that sit for a little bit, we can filter it off into a tiered round bottom flask. So we're going to tare it, but that means we're going to pre-weigh it before we add the solution, and that way after we remove the ether, we can right away just weigh the flask and we know how much compound we have isolated. So how do we remove the ether? We can maybe distill it, or if we have a rotovap, we can quickly remove the volatile solvent under reduced pressure, and we have our isolated product. Okay, so now we're ready to weigh it. We could analyze it with a variety of techniques, IR, NMR, TLC, so on, maybe GC, to see what components we have in there. And then if needed, we can purify it with other organic chemistry techniques like recrystallization or doing column chromatography or so on. So hopefully you learned something a little bit about the theory of extraction and some practical tips on how to carry out an extraction procedure in the lab. Thanks, and good luck with your experiments.
Yeah, a complete demonstration is given with the video. Next one is the different a form of advanced extractor. Okay, this is port bill neck extractor. So the mechanism is very simple, and maybe the small Asker tube, okay, will be placed, and a large Asker tube. I'll take a marker, and just the mechanical seals will be there. And this is light liquid, and this also so this HLI, okay, will be passed, okay, inside, and you can remove HLO and LLO also. So HLI, LLI, HLO and LLO indicate heavy, light, liquid in and liquid out. Heavy and light, liquid in and liquid out. Okay, that is LLI is liquid in, and LLO means liquid out. Okay, and so this is a drain, and this is a huge base, okay, will be there. And by this method, okay, we can extract continuously. And coming to the extraction process of two-phase extraction, okay, just now the video elaborated, okay, that one two-phase extraction method. And these are the different types of extraction. The reversed missile extraction, and reversed missile extraction is potentially an attractive alternative to conventional solvent extraction process, but it is very, very biocompatible. That is the advantage. And the next one is supercritical fluid extraction. So supercritical fluid extraction, okay, there are two different types. Okay, that is one is the technique of supercritical fluid extraction, which utilizes the dissolution power of supercritical fluid. That is, the fluids above their critical temperature and pressure. Temperature and pressure are the two factors involved here. And next one is the same thing, okay, explained here. And the solvent recovery, how we can recover the solvent. And this solvent recovery is possible only with the distillation process and evaporation, the removal of solvent as a vapor from the solution, and the vapor liquid separation in a column, and the condensation of the vapor. So that is explained, okay, in this diagram. So diagram of batch distillation process with the tray and the perforated plate column. So the mixture to be distilled will be heated. Okay, this is a heating jacket, it will be heated, and this is called as evaporator. And the top of the evaporator having the distillation column, and cooled with the cooling unit will be there, water cooled, or otherwise, okay, there will be air cooled distillation column. The small tray and perforated plates, okay, will be there. Okay, to that already the distillation, okay, all the components will be sedimented, okay, here, and automatically after that the vapor will go to the top, and there is a condenser will be there. Through the condenser it will be reduced to, okay, the liquid, and the fraction 1, 2, 3, how many numbers of fractions are there, and whatever how many numbers of solvents are there, everything will be collected separately. Okay, this is called as the batch distillation. And in the batch distillation also another one, okay, this is the type is, okay, the continuous separation, okay, in the different fraction 1, 2, 3, okay, will be collected, and this may be extended to n number of fractions. And coming to the continuous filtration, continuous distillation process. So this is maybe this one is heated and the vapor is passed. Okay, and if any cooling is there, automatically this will come and replace here. And this vapor through the stripping session and the plates, okay, this will go to the top, and again goes to the condenser. Condenser will be maybe the condensing the vapors, and automatically, okay, this distillate can be collected. And sometimes, okay, if you want to refill it, the reflux can be comes back to the chamber, and chamber to the heating element, and automatically this is recycled. Okay, there is no point of stopping of the product or something. And if any fluid levels are very less, automatically this will be replenished with the solvent. Okay, that will be there. And this is the explanation about okay, the continuous distillation process. So with this we can conclude the distillation. Okay, that is the solvent recovery and all. And there are two methods: batch distillation method, and continuous distillation method. So with this we can stop this lecture, and the next lecture is chromatography. Thank you.